Just to make sure we're all on the same page on our differential calculus, I wanted to have us all work through a quick pre-quiz with some questions that you might have seen in Calc 1, involving mostly derivatives and its application, its definitions, those sorts of things. If you haven't downloaded this quiz and worked on it yet, please do so. Work on it for, I don't know, about 20 minutes, half an hour if you need that much time, just to see how it goes. And then I'll work out solutions so that you can see sort of what I regard as correct answers to these problems. And if there are any gaps in what you remember from Calc 1, you can go back and review that material. All right, so let's start. For 1a here, limit as x goes to -2 of f of x. So this limit, this is just asking what happens to the function as x gets close to -2. And looking at this graph, as x gets close to -2, it looks like the graph just kind of flies upwards towards plus infinity. So this limit is positive infinity. Okay, for part B, f prime of 3. Now remember f prime, another way to write this would be df dx at 3, or depending on how you write it, some people, instead of using parentheses to denote evaluating a derivative, some people use a vertical bar like this. I think we'll usually use this notation or this notation. But a derivative on a graph, a derivative is the slope of a tangent line. So we can go to this x value, 3, so about here, and just eyeball the tangent line, looks like that, and then figure out what its slope is. So we can either approximate its slope just visually, or we could, say, pick a couple points on this line. For the purposes of this quiz, as long as you're doing something to find the slope of this tangent line, it's fine. It's not particularly important exactly what number you get. It looks like maybe if you go over 1, you go up 1.5. So that means the slope should be about 1.5, so 3/2. And this is approximate, of course. Okay, for part C, limit as h goes to 0 of f of 1 plus h minus f of minus 1 plus h minus f of minus 1, all divided by h. The thing to remember about this crazy limit of a difference quotient is this is actually the definition of the derivative of f at the x value, -1. So as long as you know that this is actually a derivative, this is the definition of the derivative, you can just go to the graph and approximate a slope of a tangent line again. It looks like it's maybe -0.5, something like -0.5. Okay, so again, the important part out of this one is just that you know what the limit definition of a derivative is. All right, so for number 2, just calculating some derivatives. So whenever I go to calculate a derivative, the very first thing I do is I sort of figure out how this expression is put together. So this first part is x squared times sine of 5x. So when you're taking a derivative, you sort of work from the outside inwards. So the furthest operation outside is this multiplication. So when we do the derivative, we have to deal with the multiplication first, and we'll deal with it by using the product rule. So we need the derivative of the first part, which is x squared, times the second part with no derivative, plus the first part with no derivative, that's x squared, times the derivative of the second part. So derivative of sine 5x. Okay. Now this clump of symbols, this ddx, if you are used to this d notation for derivatives, you're probably used to seeing it with some function, maybe an f or a y up here. But when that isn't there, this just means take the derivative of. So it's like a verb, take the derivative of. Okay. So something like df dx, that's a noun. That is the derivative of f with respect to x. But ddx, that's a verb or a command. It's telling you to take the derivative of whatever follows it. So since I needed some way to express the derivative of x squared, I used this ddx notation. Of course, we actually need to evaluate this derivative. So derivative of x squared is 2x using the power rule times sine 5x plus x squared times, and now the sine of 5x, sine 5x has an inside and an outside. The inside part is 5x and the outside part is sine, and so we need to use the chain rule, right? The chain rule says take the derivative of the outside part, so that's cosine. You put the inside part into it, and then you multiply that by the derivative of the inside part, and the derivative of 5x is 5. All right, so there is our derivative for part A here. All right, now for part B. Looks like we have a quotient, so we should use the quotient rule. If you wanted to, you could convert this quotient to a product using a negative exponent and then use the product rule, but let's use the quotient rule. So g prime is, so I guess technically g prime of x is derivative of the top, so derivative of e to the x is e to the x, times the bottom with no derivative, so natural log x, minus the top with no derivative, that's e to the x, times the bottom with the derivatives, derivative of natural log x is 1 over x, all divided by the denominator squared, so natural log x squared. All right, now we would simplify this if there were any simplifying to do, but I don't know that there's really any way to make this any simpler. I mean, maybe you could multiply the numerator and denominator by x and distribute this in the numerator just to get rid of this 1 over x, but I don't know, that's window dressing. It doesn't really do a great deal in making this function look any prettier, so let's just leave it. All right, number 3, find the equation of the tangent line for this function at x equals 1. So the thing to remember about a tangent line is there's a different tangent line at every x value, right? This function is some cubics, so it looks something like this, right? Probably not exactly this, but, and you can see at every point on this function, the tangent line is actually a different line. Well, at most places anyway. So when we find the tangent line, right, since we're finding the equation of a line, right, that's going to be something like y equals mx plus b, or, you know, whatever form of the equation of a line you want, but it needs to be the particular tangent line for this x value. Okay, so this is at x equals 1, so maybe that's right here. So for this particular tangent line, we need to know the slope of this tangent line and a point for this tangent line. Well, a point on the tangent line is that point on the function. So that's going to be the x value that we have, comma, well, to be on the graph of this function, the y coordinate for this point had better be the function at that x value. In other words, we need to evaluate this function at the x value that we have. So this is going to be 1 cubed minus 4 times 1 squared plus 1, you know, do the arithmetic. So 1 minus 4 plus 1 minus 1. So it looks like this is going to be 1 comma, let's see, these undo each other, minus 3. 1 comma minus 3. All right, so this is a point that is on the line that we want. Now we need a slope for the line that we want. And since it's a tangent line, it's a tangent slope. And so we should use the derivative. So first, let's calculate the derivative. So the derivative is just using the power rule, 3x squared minus 8x plus 1. Okay, so this will tell us the slope of any tangent line, but we need the slope of the tangent line that we care about, which is at x equals 1. So we have to take this derivative function and plug in x equals 1, and this is going to give us 3 minus 8 is minus 5 plus 1 is minus 4. Okay, so now we have a point on our line and the slope of our line. So now we can write the equation of our line. I'll write the point-slope equation just because I have a point and a slope. So that's y minus the y-coordinate of the point, which is negative 3, equals -4, the slope, times x minus the x-coordinate of the point, which is 1. And then if you want to simplify this equation or put it into slope-intercept form, you can. So let's see, to simplify, maybe we would cancel those minus signs. So, and then if you want slope-intercept form, you're going to get y equals -4x. Let's see, I'm distributing this -4 here. Y equals -4x plus 4, because we get -4 times -1. And then this 3, we need to move that to the other side, so that's a -3. So it looks like the equation for the tangent line is y equals -4x plus 1. Okay, there we go, we're done. All right, last question on this practice quiz. So object's velocity in the vertical direction, so it's moving up and down, and its velocity is given by 1/10 t squared minus t plus 3, and that's in meters per second, which makes sense because that's a velocity unit. If the height of the object at time t equals 0 is 100 meters, find the height as a function of t. So we're trying to find the height as a function of t. And we know, the derivative of the height function, if you have a position function, its derivative is velocity. And we know this velocity function, we have a formula for it. So what we need to do is come up with some function. We need to undo this derivative to turn this velocity function that we know into the height function that we want. So we just need to come up with some function whose derivative is this given velocity function, 1/10 t squared minus t plus 3. All right, and this idea of undoing a derivative, basically you just use all the experience you have from evaluating or from calculating derivatives to guess a function that would have this as its derivative. So we're basically going to guess. It's not random guessing because we have a lot of experience calculating derivatives. So we have a good idea of what to guess for h to make this its derivative. So t squared, if that t squared is from a derivative, that means it had to have come from t cubed. But then to end up with, if we take a derivative of t cubed, this 3 would come down, but we're supposed to end up with 1/10, so we'd better have 1/30 here. So now if you took a derivative, this 3 would come down and make this 1/30, 1/10 t squared. So that first part is done. And then minus 1/2 t squared plus 3t. And then something to remember about undoing a derivative like this is there's always a constant that you don't know. There's always this arbitrary constant because we can check that this is the correct way to undo the derivative because we can take the derivative of h and see if we get this function for v. And we do. If you calculate the derivative of this h of t that I've written down, you do get the v of t that we started with. And critically, this constant, its derivative is 0, and so when you take a derivative, whatever this constant was, it doesn't matter for the velocity function. So this constant really could be anything. But we have an initial condition. The height of the object at time t equals 0 is 100 meters, and hopefully you remember that when you're undoing a derivative, it's an initial condition that determines what this unknown constant is. So now that we have a partial formula for h of t, we can use this initial condition to find capital C. And you use the initial condition by plugging it into the function. So where the t value here is 0, and we know that h of 0 ought to be 100 because the object is at height 100 meters when time is 0. But on the other hand, we have a formula for h, so we can plug in t equals 0 into this formula, and we get 0 from this first term, 0 from the second term, 0 from the third term, plus c. And so this gives us an equation that tells us what c is. C is 100. And now that we know what c is, we can write down our height function. It's 1/30 t squared minus 1/30 t cubed minus 1/2 t squared plus 3t plus c, which we now know is 100. And so there's our height function. If any of the solutions from this Prequiz mystified you, or if there are any gaps you think you have in your knowledge in what you remember from Calc 1, now is the time to go back and do some review so that you can really hit the ground running when we start using all of this when we hit new course material.